Welcome back everyone, Patrick here, moving on to another question very similar to the previous question, where what we have to do is we have to take these patterns here. So notice in this case there's two, in the previous one there was only one. And what we have to do is we have to find an expression for the number of shaded squares in the nth diagram. So for this first pattern, this is the first diagram, second, third. For the second pattern, first diagram, second, third. Now, when I'm doing these questions here, I'm assuming that you've watched the previous video, the first one that we just did. If you're watching this on YouTube, you can go to the website. The link to the website is in the description box, and I recommend following the videos in order because there's a lot of carryover that goes through the videos. So again, when I'm doing this, I'm assuming that you've watched the previous video. It's just going to be right above this one on the website, because I'm going to go through the exact same process. This one's going to be a little bit more complex, especially B, but it's still going to be the same process of where we're going to create that total column, the unshaded column, and then the shaded column. So I'm going to erase B for now. I'll bring it back later in the video once we get to it, once we finish A. So let's start off with this over here. So like I did in the previous video, the way I do these is I create a column for the diagram number, because the expression, that's what it's going to be based on. So the diagram number, that's going to be n, right? We're basing it on the nth diagram. So this here is going to be the first diagram. So in this case, n is 1. Here, this is going to be the second diagram, so n is 2. Here, this is going to be the third diagram, n is 3. So that's the first column. Now, the second column, if you remember, what I do is I create a total squares column. You can, because we're finding the number of shaded squares, you can create just a shaded square column and then count over here. So we got like 1, 2, 3 shaded squares for the first diagram. Here we'll have what? 7 shaded squares, and then over here we'll have what is it going to be? 13 shaded squares. But as I mentioned in the previous video, a lot of times it's tough to figure out the relation just from that column alone. Right? Versus if you make a column for the total, and then you make a column for the unshaded amount of squares in each diagram. Let me erase these over here. The total number of squares minus the unshaded number of squares is going to give you the shaded number of squares. Okay, so for example, this first diagram, when n is 1, how many total squares are there? Well, notice there's 2 by 2, so there are 4 over here. How many unshaded squares? There's only this one unshaded square, which means that the total number of shaded squares is going to be 3. So you could directly count them, or you could just go 4 minus 1, which is going to give you that 3. So different ways to go about it. The second diagram, notice how many squares are there. Well, it's 3 by 3, so the total is 9. How many unshaded squares? There's only these 2 over here. And so the total number of shaded squares is going to be 9 minus 2, which gives us 7. Or again, you could just directly count them, right? But as the diagrams get bigger and bigger, perhaps counting this, because there's a lot more shaded squares versus unshaded ones, counting them can sometimes get a little bit cumbersome. But this is not too bad, so we can do both just to fully check our answers here. So this is the third diagram. What's the total number of squares? Well, notice there's 4 and then 4, so 4 by 4 would give us 16. Then the total number of unshaded squares is going to be 3. And so 16 minus 3, as we mentioned before for this diagram, is 13 for the number of shaded squares. But if you want to count it, 3 by 4 for this area, which gives us 12, plus this 1 over here, which gives us 13. So now what we got to do is we have to figure out a pattern here for the nth diagram what's the number of shaded squares going to be? We have to create some kind of expression over here, right? So we're going to let that be S like we did in the previous video. Now, directly going from here to here, trying to find out that pattern, notice it's going to be a little bit difficult, right? So how does the 1 relate to the 3? Well, there's a bunch of ways it could relate. We can maybe multiply this by 2 and add 1, or we can add 2 to this, right? It's tough to see. But then when we go from 2 to 7, it's got to relate in the same way. So how does 1 relate to 3? Well, a bunch of different ways, but then how does 2 relate to 7? Well, we could add 5 to it, but then we're not adding 5 to the 1 to get to the 3, right? Or we could take the 2, we can multiply it by 3, and then add 1, so 2 times 3 is 6, plus 1 would give us 7, but notice we're not doing that here, right? If we take the 1 multiplied by 3 and add 1, that would give us 4. That's not going to give us this 3. And then we have to make sure that the 3 relates to the 13 the same way. So it's kind of tough to see the relation or to get the relation directly from this column to this column over here. But notice that with these two columns, it's a little bit more clear with what's going on. Notice that there's 4 over here. And how did we get this 4? Well, notice that there was 2 by 2. So we can actually write here 2 to the power of 2. That's how we got this 4. And then this 9 over here, notice it was 3 by 3. So it was like 3 to the power 2. And then how did we get this 16? Well, 4 by 4. It's like 4 to the power of 2 over here. So we could kind of see a pattern here with the 4, 9, and then the 16. I'll talk about in a sec how to relate it to this, but nevertheless, we do see a pattern, right? 2 to the power 2, 3 to the power 2, 4 to the power 2 over here. Versus here, we're not seeing that pattern clearly. There is a pattern, it's just not clear. Versus here, notice the unshaded number of squares. Well, that pattern is super clear. It's 1, 2, 3. So we could be pretty confident that the fourth diagram is going to have 4 unshaded squares, right? It's just going up by 1s over here. And then for this, instead of directly going after it, all we're doing is we're taking this minusing this over here. So let's try to create an expression for the total number of squares and then the unshaded number of squares for the nth diagram. And then once we have those over here, we can just subtract them to get that shaded number of squares relation. So let's start off with this column, this total column here. So how can we relate this 1 to this 4, or this 2 to this 9, 3 to 16? Well, a lot of times what you want to do is you actually want to rewrite these like this, because it's kind of tough to see how to go to 1 to 4, but notice it's easy to see how to go to this base of 2 from 1, and then from this 2 to 3, and then from this 3 to 4, all we're doing is we just add 1 to these and then square it. So sometimes actually what you can do is you can actually add another column. So you could have this total column, but another column you could add sort of here, let me just write it over here, is if these are squares, notice that they are squares. All of these are squares, meaning that the length and the width are the same, right? It's just one length. This one has a length of 2, this one has a length of 3, this one has a length of 4. You can kind of, sorry, not base, let's put length over here. You can see that the length over here is 2. Over here, the length is 3. And then over here, the length is 4. Right? And then from here, you could see that we're just adding 1 to each of these to get the length. But then for the total number of squares, what we're doing is we're taking that length and then we're squaring it. So if you do want to add another column here for the length, especially if you're dealing with squares, because both lengths are going to be the same, If you start dealing with rectangles, then it might be worth it to make a length column and then a width column. And then you got to work with both of those separately. Actually, I just thought about now that might be a good example to do for a future video. But luckily in this case, for both cases in part B as well, we're just dealing with squares, so we can just create one length column over here. And again, you don't necessarily have to. You can just kind of put the total over here, but then you can put on the side how we got that total, right? And then from here, you can see we're just adding 1 to get that length, or to get that base over here. And so to create a general expression for the nth diagram, what we can say here is it's going to be n plus 1 to the power of 2, like that. Okay, so n plus 1 to get the length of the square, and then we are squaring it to get the area, or the total number of squares. And again, you could test this. So if we're on, here, let me just erase this. There's a lot going on. And let me, you know what, I'm going to erase this as well, just because we got this from writing those out. And now let's just test it. For the first diagram, that would be n is 1. 1 plus 1 gives us 2. 2 to the power of 2 would give us 4. 2 for the second diagram, n is 2. 2 plus 1 gives us 3. 3 to the power of 2 gives us 9. 3 for the third diagram, n is 3. 3 plus 1 gives us 4. 4 to the power of 2 gives us 16. So we can be pretty confident that for the fourth diagram, it's going to be 4 plus 1. There's going to be a length of 5 for the square. And so the total is going to be 5 to the power of 2, which would give us 25. And you could just keep going like that. So that's the general pattern here for the total number of squares, depending on the nth diagram. I think in the example before, it was just n squared, right? We were just taking these and squaring it. Well, now we're adding 1 to get the length and then squaring that in order to get the total, right? So the relation for this column is n plus 1 in brackets to the power 2. That's how the total number of squares relates to the nth diagram. Okay, now let's go here. What about the unshaded one? Well, this one's super easy. For the first diagram, there's 1 unshaded square right here. For the second, there's 2 unshaded squares right here. For the third, there's 3 unshaded squares. So then for the fourth, how many is there going to be? 4, 5, 5, 6, 6. For the nth, there's just going to be n right there. Right? So this column and this column, in this case, they're the exact same thing, which is nice. So for the nth diagram, there's going to be n unshaded squares like that. And so now it's easy to get this because we know it's just this minus this the whole time, right? So it's basically for the nth diagram, it's going to be the total n plus 1 to the power 2 minus the unshaded to get the shaded number of squares. And as I mentioned before, notice if we tried to get it directly without these columns, it would be kind of tough to be able to get this, right? Just directly straight away. And knowing that we have to add 1 to this, then square it, then we have to subtract this same number. Okay, it would be tough to directly get that, but over here, we're able to directly get it, because we know it's just going to be this column minus this one. Now this here isn't simplified, so let's actually simplify, because the answer for a question like this is going to be simplified, right? It says find an expression. It should say find an expanded expression, but it's okay. Let's just simplify here. So how do we simplify that? Well, the n plus 1 to the power 2 is going to be n plus 1 times n plus 1. And we're going to subtract n. So n times n is n squared. N times 1 is 1n, or just n. 1 times n is n. 1 times 1 is 1. And then we're subtracting an n right there. And so from here, collect the like terms, which is this, this, and this. Actually, one of these just cancel out with one of those. So we're just left with an n. It's going to be n squared plus n plus 1. That's going to be the yes, the number of shaded regions, right? The number of shaded regions, which is this S, for the nth diagram. And then if you want, if you have time, check this. What we can do is, notice we have values here we could check. So if we plug in 1 for n, 1 to the power 2 plus 1 plus 1, that's going to be 1 plus 1 plus 1. That's going to give us 3. What about for the second diagram? We'll have 2 to the power 2, which is 4, plus 2, which gives us 6, plus 1 gives us that 7. What about for 3? 3 to the power 2, 9, plus 3, 12, plus 1 gives us that 13. Right? So once you get this final expression here, check with the numbers you have in this column, just to make sure that everything is working out. Because getting these expressions is not too bad, but sometimes maybe even the algebra, you might make a mistake in the algebra, and so checking your answer would help you catch that. Now moving on to part B. So again, notice that we got 3 diagrams here. We have to create an expression for the number of shaded squares in the nth diagram. So again, n is 1 here, n is 2, n is 3. We got to create that same expression, the number of shaded squares. We're going to let it be S is equal to some kind of relation in terms of n. So same thing. I'm going to first create some columns here just to see if we could catch any patterns. So we're going to have the diagram number. This is going to be n. Now, in the previous example, I mentioned how you can create another column called the length and then the width. In this case, as I mentioned in that part A, we're dealing with squares here. We dealt with squares in the previous video. We also dealt with squares in part A, and we're dealing with squares over here because notice that the length is the same, right? The length and the width are the same, 2 by 2. Over here, it's going to be 4 by 4. Over here, it's going to be 6 by 6. Okay, so what I'm going to do is I'm actually going to create another length column. I could have maybe did that for the previous ones as well, but the previous ones weren't too bad. In order to get an expression for that total column, this one's going to be a little bit more tricky. It's still not going to be too bad, but I feel like there's going to be a little bit more going into this one to find that total column. And then also, again, we're dealing with squares, but there can be questions, and I think I'm going to make a question where you could be dealing with rectangles, where this length and this width, they're not going to be the same. And then you for sure want to make 2 different columns for that. Okay, but luckily we're still dealing with squares, so the lengths are the same. The length and the width are the same, so we could just have one column. And then what we're going to do is we're going to have a total column, which is just going to be this value to the power of 2. Right? It's going to be 2 to the power 2 here, which would give us 4. Or here it's going to be 4 to the power 2, which is going to give us 16. And then we're going to have the unshaded column, the total of unshaded squares. And then when we subtract the unshaded from the total, we're going to get the shaded over here. So let's create this table here based on these diagrams. So for this first diagram, the length is what? It's 2. And then the total number of squares is going to be 2 to the power 2, which would give us that 4 over here. Now, what's the number of unshaded squares? It's going to be 1, 2, and 3. And so the number of shaded squares is going to be 4 minus 3, which is 1. And we can confirm that there's only one shaded square over here. What about for the second diagram? Well, for the second diagram, notice that the length is 4 on each side. So the total is going to be the length squared, which is going to be 16. The unshaded number of squares is going to be 1, 2, 3, 4, 5. And then 16 minus 5 would give us 11. And then we can confirm that 11 if we count 1, 2, 3, 4. There's 2 rows of that, so 8, 9, 10, 11. right? So it makes sense over here so far. And then for the third diagram, what's the length? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So the length is 6, meaning that the total is going to be 6 to the power 2, which gives us 36. The number of unshaded squares, 1, 2, 3, 4, 5, 6, 7 over here. And hopefully you're catching the pattern here for the unshaded. Notice it's just the bottom row plus 1, right? The bottom row plus 1, bottom row plus 1, bottom row plus 1. So then the number of shaded squares here is going to be 36 minus 7, which would give us 29, like that. And then again, you can confirm this. There is 6 in each row. 1, 2, 3, 4 full rows. So that's 24, 25, 26, 27, 28, 29. All right, so that is the table of values for this pattern here. So again, what we have to do is we have to create an expression for this, the number of shaded squares. We're going to let that be S in terms of n. Now, trying to directly do it, how does 1 relate to 1, and then 2 relate to 11, and then 3 relate to 29? It's fairly complex, right? So again, as I mentioned before, I wouldn't recommend directly going here. I would recommend working with these columns first, and then if you could get these two columns down, well then this is just going to be the difference between those. So let's actually start with the length over here, right? This is why I wanted to create this, because notice that the length is jumping a lot more than just 1. Before it was just jumping by 1 in the previous two examples. Now it is jumping by 2. And so how does the length of each of these squares relate to the diagram number that we're on? Well, how does 1 relate to 2, 2 relate to 4, 3 relate to 6? Well, it seems like we're just multiplying these by 2 in order to get this over here. And so that means for the nth diagram, we're also going to be multiplying it by 2 to get the length of that square. 2 times n, that would just give us 2n. Like that. So the length for the nth diagram is 2n. What we're doing is we're taking the diagram number, multiplying it by 2 in order to get that length of the square. So the fourth diagram, it's going to have a length of 8. It's going to be 8 by 8. And then the total, we know how we're getting the total. We're just taking these and we're squaring it because it's just the length times the length. The area, basically. 2 squared, or 2 times 2, gives us 4. 4 times 4, 4 squared is 16. 6 to the power 2, or 6 times 6, gives us 36. So if a square has a length of 2n, how are we going to get the total? Well, we're going to take that 2n and we're going to square it. Just be careful, that's got to be in brackets right there, because we're squaring that entire amount here. So if you wrote just 2n squared, that would actually be wrong. And then you could test it. So for example, again, let's deal with the fourth diagram. The fourth diagram, it's going to have a length of 8, so it's going to be 8 by 8, which would be 64, right? But if we plug in 4 over here, 4 to the power 2 would give us 16 times 2 would give us 32. It wouldn't give us that 64. So that 2n, it has to be in brackets. That's one of the tricks for this particular pattern over here. And then if we use this, 2 times 4, we got to work with the bracket first. It's 8. 8 to the power 2 would give us that 64. Okay, and then again, you could test these over here as well. 3, if we plug in 3 for n, 2 times 3, 6 to the power 2. If we plug in 2 for n, 2 times 2, 4 to the power 2 gives us 16. So check these expressions that you're getting with the values in the column that are already there. All right, but this is what it is for the total right here. So for the nth diagram, the total number of squares, or the area, is going to be 2n in brackets to the power of 2, like that. Now, moving on to this column, what about the unshaded number of squares? Well, as I mentioned while I was writing this, you can see the pattern from the diagram. The unshaded squares, notice that the bottom is always unshaded, and then there's one extra one that's unshaded as well. So it's like, if you think about it, the unshaded number of squares, it's like the length plus 1, right? It's 2, the length over here, 1, 2, plus 1. Here it's 1, 2, 3, 4, plus 1. The length was 4 for the second diagram. Here the length is 6, so it's 6 plus 1, like that. So it's just the length plus 1. And so the unshaded number of squares here, it's actually just the length, which is 2n plus 1, like that. Right? So you got to kind of look at the diagram in order to get that. And notice that this here, I didn't mention this in the previous examples, but notice this is a linear relation, 2n plus 1, right? It's like y equals mx plus b, and notice that it's going up by a consistent amount, which is the slope, which is just this 2 over here. 3 plus 2 is 5, 5 plus 2 is 7, etc., etc. So it's a line. This is a linear relation, right? Versus this here, this is a quadratic relation because we have this square here. And then when we combine these, the relation here, it's going to be a quadratic because it's always going to be the highest degree with whatever you combine. You can combine a quadratic with a linear, but that combination is still just going to be a quadratic. All right, so again, I feel like this one is a little bit more tricky than the other ones. There's a little bit more going on, especially with this length over here. So that's why I wanted to create this other column in order to get this. And the unshaded number of squares, it's a little bit more complex as well, right? We're not just like adding 1 to these, or it's not the same as it was in part A, right? It's a little bit more of a complex pattern. We're taking, the bottom is always unshaded, so the length, so 2n, plus there's always one up top that's also unshaded on top of that bottom column. Now you might get 2 that are unshaded, right? So then it'd be 2n plus 2, right? So just be on the lookout. You got to kind of look at the diagram and really make sense of everything. And then again, you could check this. So we can, if n is 1, plugging 1 here, 2 times 1 is 2, plus 1 gives us 3. If n is 2, 2 times 2 is 4, plus 1 gives us 5. If n is 3 for the third diagram, 2 times 3 is 6, plus 1 does give us 7. So it does check out with the numbers that we also have. And then the shaded column, we know it's just the total column minus the unshaded column. So it's actually just going to be this 2n squared minus, be careful here, you're subtracting that whole thing, right? So you're not just putting minus 2n plus 1, you got to put the 2n plus 1 in brackets. We're subtracting that entire expression. All right, so lots of tricks on the way to the final answer for this kind of question. So this is a really good thinking kind of question that can come up on a test. But if you do get something like this, I recommend breaking it down like this. It might take you a little longer, but if you try to directly get to this, it's a little bit tough. You can do it, but I feel like you'll get it quicker creating these extra columns over here. Now this is definitely not simplified, right? The teacher's not going to allow you. Maybe some will. I wouldn't personally. I would want that simplified. So we have to simplify this. So let's actually write it. S equals 2n squared minus 2n plus 1 over here. This is another trick for the question. It's not just n squared, it's 2n squared. Now, a review of exponents, if you got two things that are multiplying and then you got an exponent, well, you could take both things to that exponent. If they're multiplying or dividing, if it's a fraction, you could take the numerator to that exponent, denominator to that exponent. So that's what we have to do here. We have to take the 2 to the power 2 and then the n to the power 2. Here we have to distribute the negative like that. So what would we get? 2 to the power 2 is 4, n squared minus 2n minus 1. And then there's no like terms to simplify. So that ends up being the final answer. And again, if you want to check this, notice I kept that shaded column over here. So let's say for n is 1, for this first diagram, if we plug in 1 for the n values, we'll have 1 to the power 2, which is 1 times 4 gives us 4. Minus 2 times 1 is 2, minus 1. So we'd have 4 minus 2 minus 1, which would give us this 1 over here. What about when n is 2? So if n is 2, we got to do the exponent first. 2 to the power 2 would give us 4. Times 4 would give us 16, minus 2 times 2 would give us 4, minus 1. 16 minus 4 is 12, minus 1 does indeed give us 11. And then finally, for an n value of 3, plugging in 3 here, 3 to the power 2, 9. 9 times 4 would give us 36, minus 2 times 3 is 6, minus 1. 36 minus 6 is 30, minus 1 gives us that 29. All right, so once you get your final answer, check it with the amounts you have in the diagram. All right, so for these kinds of questions, this is the process that I personally go through, and this is the process I recommend you going through, creating a table of values for the total, the unshaded, the shaded, and then combining them, and then getting your expression.